or chloride so that the copper cannot be dry etched. That is one of the problems with the copper. So in most VLSI processes for the metallization, instead of copper, aluminum is used because aluminum form a chloride to be etched or fluoride to be etched. That is the reason why the copper is not used for the metallization in VLSI, even though copper has a lower resistivity than the aluminum. Well, this is an example of the etching elements, and you can see most of them consist of the fluoride form. Okay. For example, the titanium can be etched by CF4 gas, things like that. Okay. The plasma is a simple means of obtaining atomic F. So that is why we try to form a plasma. Okay, that atomic F is working to etch the substrate. Okay, the lifetime means before it recombined to form a stable form, like a CF3 combines with F and to form a CF4. Okay, and when it is fragmentized by the plasma, it is not going to stay that way for a long time. It tends to recombine after a certain period of time, and we call that time is lifetime. Okay, and lifetime is 0.3 seconds. So after 0.3 seconds, the fragmentized CF3 gas and F atoms is going to recombine to form a CF4. So if once it is formed the CF4, it is not going to work as an etchant at all. So everything has to be done within a 0.3 second, in other words. Diffusion coefficient, 500 centimeters square per sec at the room temperature, and 1 torr. Of course, that is the diffusion coefficient is very much related to the pressure of the chamber of the plasma, right? Therefore, the F can travel about 25 centimeters before recombination takes place. So the plasma and your the substrate to be etched, the distance has to be within 25 centimeters. Okay, that is the point here. Geometry of a system must place the plasma close to or in contact with wafers. The other extreme, from a purely chemical process, as discussed. We have discussed, so far we have discussed about the chemical process, right? The atomic F reacts with the silicon to form a silicon tetrafluoride, which is a gas, so that it is going to be etched. The chemistry involved in the dry etching is exactly the same chemistry that happens in the wet etching. Okay, in wet etching case, the fluorine ions is going to react with the silicon to form a silicon tetrafluoride, which is a gas, so that you can see the bubbles coming out from the surface of the silicon wafer, for example. Okay, the same thing happens in the plasma chamber when the chemical process is involved. But the other extreme, which is going to be described here, is the sputtering, which is a purely physical process. It does not involve the chemistries at all. Okay, what we do is we going to use a argon, which is inert gas. It's not reactive gas at all. Okay, very stable argon gas, and then we apply the high voltages, RF voltages. Then it's going to ionize to form a plasma, like argon plus and electrons. And that argon plus is, since it is ions, it has a charge. When you apply the RF during the two electrodes, between the two electrodes, then ions are moving very slow comparing to the electrons. So that even if you apply the AC between the two electrodes, you can find the DC characteristic inside it. Because ions, which is positively charged, and electrons, which is negatively charged, they are moving differently. So they form a bias in itself, and we call that the self-bias. Self-bias. Okay. So even if you apply the radio frequency AC between the two electrodes inside the plasma, you can see the DC characteristic inside it because of the mobility difference between the ions and the electrons in the plasma. We call that the self-bias. And with that DC characteristic, the ions is going to feel the field. So it has a directions. It is going to move towards the negative directions. So if you place your substrate and negatively grounded part, then the argon plus is going to be accelerated with the self-bias, and then it's going to hit the surface atom to take off. We call that the sputtering. Okay. In that sputtering process, no chemistry is involved, so that is the physical collision only. Now, if we accelerate the argon ions at the high energies, we call that implantations. Okay, the argon ions is going to be implanted inside the substrate. That is the implantation. If we accelerate the argon ions less than the sputtering energy, then we call that electroplating the atoms. And the argon ions is going to be placed on top of the substrate, and we call that electroplating. So depending on the energy of acceleration, we can have electroplating, and you have more accelerated energy, then we are going to have a sputtering. And if you accelerate the ions more, then we are going to have an implantation of the energies. Okay, the sputtering is in between, so that like a billiard balls, they collide the surface atoms and then take off the surface, various surface atoms. Argon ions are accelerated to the substrate and the physically sputter atoms off. Okay, this process involves no chemistry, just the physical collisions. In fact, most of the dry etching technique involves some physical and some chemical component to the etching. And then at the end of this lecture, I'm going to compare all different dry etching techniques, and you can see the portions of physical etching to the chemical etching is changing depending on the technique. Now let's start with the barrel type reactor. Okay. The barrel type reactor, it looks like this. Okay, it has, you can see the perforated shield. That is the characteristic of this barrel type reactor. You have wafer at the center, and then you form a plasma, and the distance between the plasma and the wafer should be less than 25 centimeters because of the lifetime. If it is longer than that, then you are not going to have any etching with this barrel type reactor. Ions are kept away from the wafer by shield. Neutral species diffuse to the wafer, and as we have estimated, 25 centimeters. And the etching is purely chemical, so that we are going to have isotropic etching, just like the wet etching in this case. There is no physical acceleration of the etchant atoms at all, okay? And this is important, the low cost, it's just a barrel. It doesn't have nothing but the barrel, okay? Low cost, high throughput, and the pressure is important here. The pressure is just 1 torr. And this is general feature. You're going to have a reactant or etchant, long life etchant, short-lived etchant. Short-lived etchant means it has a short lifetime, okay? And then it has just a direct etchant, nothing to do with the lifetime. So we can see the 3 types of etchant, and the long-lived etchant is going to contribute to the undercutting mostly. Okay, undercutting happens because of this long-lived etchant. Okay, and this short-lived etchant is also makes some undercutting, but not that much like long-lived etchant. And this direct etchant is nothing to do with the undercutting. Okay, it's directly etched to the directions, illustrating the effect of different types of reactive particles on the etching profile. The photomasking specimen to be long-lived neutral radicals are L, this is actually L, and short-lived neutral radicals RS, and I are incident at right angles and do not give any undercutting. Well, this is just you can easily understand this, right? This is what happens. In a barrel type reactor, only neutral species, that is RL, okay, long-lived radicals are involved. So we have isotropic etching, large undercutting, just like the wet etching, and it's just a drying process, but the etching fashion is almost the same to that in the wet etching, okay? Practical reactions, let's see. We are going to have a fluorine gas, and then we add the oxygen here, and then you can see we are going to have a fragmentized F atoms here, which is going to be used as an etchant. Okay, that F is going to react with the silicon to form a gas, silicon tetrafluoride. That is a gas, so that it just take off the silicon with this chemical reactions A. And in case of a nitride, it form a silicon tetrafluoride, which is the gas again, and then it's going to be etched. Now this is the photoresist, the chemical composition of the photoresist, and this photoresist you are not going to use any fluorines. Just the oxygen atom is going to react with this photoresist to form CO2 gas, just like this. We call this the burning, in the oxidation or burning. Just the burning of the photoresist, burn out. Okay. So we can use the fluorine gas and oxygen gas combination to add to silicon and nitride photoresist. And a series of experimental results will show you how effective these barrel type reactor can work. Okay, this is the first result, and the etch rate in the y-axis and the oxygen content, CO2, the content of oxygen content in the axis. Then you can see as you increase the concentration of oxygen in the carbon tetrafluoride gas in the plasma, okay, then you can see monotonic increase, exponential increase, because it's a logarithmic scale in the y-axis, okay? Exponential increase at a certain, let's see, about the 3 to 4% of oxygen addition, but after that, the etch rate is going to be saturated. And the silicon oxide, that star, this is silicon oxide, is a thermal oxide that we have discussed. But the silicon oxide, the star, is pyrogenic silicon oxide. Silicon gas and oxygen gas, they react to form deposition. Okay, so this is not thermal oxide. This is the deposited oxide, and this is thermal oxide. You can see the difference in the etch rate. Anyway, so you can see the enhancement of the etch rate with the addition of O2, oxygen gas, and that's because the reactions here in this is the reaction happens in the plasma, and if you add the oxygen, then the more chemical reaction occurs to the right hand side. It promotes the reactions. That's why the oxygen addition will increase the etch rate, but if you add more than 3 to 4% of oxygen, then that oxygen is going to dilute the CF4 gas itself, so that it is going to be saturated. The etch rate is going to be saturated, as you can see here. Okay? So, this is the SiO2 star, refers to the silicon dioxide that has not been prepared by the thermal oxidation of the silicon, but by a gas phase reaction between silane gas and an oxygen at the low temperature, and it has the etch rate is higher than the thermal oxide. In other words, the thermal oxide is a more dense material. The experiments were performed at a gas pressure, okay, and increasing. This is not the CO2 concentration of oxygen, so you have to write concentration and the subscript O2. This is also, we do not have any carbon dioxide. No carbon dioxide, okay? From 0 to 2 or 3% gives a large increase in their etch rate, but at still higher values of oxygen concentration, the value R remains constant. That's what you can see here. And O2 is added to the CF4 gas to increase the amount of atomic F produced and hence increase the H rate. That's obvious. And here, this is the practical numbers. And note that these systems cannot be used to etch silicon oxide on silicon because the selectivity is 1 to 15. It means that if you have a silicon substrate and then you have a, for example, thermal oxide on top, and then you want to etch, make a pattern of the silicon dioxide, silicon oxide, which is deposited on top of the silicon. And then for that, if you use the barrel type reactor, then you can see the etch rate of silicon oxide is 80 angstrom per minute. But the silicon oxide, polysilicon is 1200 angstrom per minute, which is very much faster than that of silicon oxide. So in that case, when you etch the certain silicon oxide on the top, then you have to stop immediately right after the silicon oxide etch. Otherwise, the substrate, the silicon, is going to be etched very fast, much faster than the silicon oxide. So in that, if that is the case, we cannot pattern the silicon oxide with this barrel type silicon, barrel type CF4 plasma. Okay? If the etch rate is the other way around, then we can etch the silicon oxide. Because even if after we complete the etch of the silicon oxide, the plasma is going to continue etching the silicon, but the etch rate of a silicon is very much slower. If it is much slower than the silicon oxide, then we'll have some safety margin. We don't have to worry too much. But as you can see in this case, the selectivity is 1 to 15. Then we have to stop silicon etching the silicon oxide right after at the exact time. Otherwise, the substrate, the silicon, is going to be etched much faster than the silicon oxide. In that case, we cannot use this barrel type CF4 gas to etch the silicon oxide, which is deposited on top of the silicon. Okay? The selectivity means that etch rate of the various materials with temperature is plotted in the next slide here. This is the reciprocal temperature. Okay? So this is the low temperature, and this is the high temperature, and this is the etch rate. You can see the activation energy is about 0.1 to 0.2 electron volts, and etch rate are and this particular example, you use 4% of oxygen in the CF4 gas, which has been shown here. Well, yeah. You here here this CF4 gas containing 4% of oxygen at a gas pressure of 133 Pascal. RF plasma power is 100 watt. Flow rate of fluorine gas is 300 centimeter cube per minute. And you can see the straight line here. This explanation is belonging to this figure. Okay? And you can see the straight lines. And this explanation is belonging to the top figure there. This is, sorry about the confusion here. And this particular example is a silicon nitride etch. This is a silicon nitride etch, and the 8% of oxygen is used, and compared with the no oxygen case. And one thing you can notice here is that the straight line both has the same slope, even though the etch rate is different, but the slope is the same. And that signifies here, even with the oxygen added to the CF4 mixture, the silicon nitride etch rate is the same, indicating that the chemistry has not changed for the etching, right? Just more alpha is produced in the plasma with the addition of the oxygen. Note that the chlorine-based processes are not often used in a barrel-type reactor because many of the reaction products are too short-lived. Okay, so that this means the wafer and the plasma, the distance between those two has to be less than 25 centimeters if you use the chlorine as a reactive gas, plasma gas. And besides this, chlorine is very corrosive, so that we do not want to the chlorine in your, we do not want to flow the chlorine in your chamber. Now let's move to the planar type reactor. And this is the summary of the barrel type reactor. The way to read this is that the etched silicon nitride on top of the silicon oxide, the selectivity is 4:1. So I think 4:1 it is the bottom edge selectivity. So maybe you can use this gases to etch the silicon nitride, which is deposited on top of the silicon oxide. When this is the case, the local oxidation, locus process, you form a base oxide, 300 angstrom of base oxide first, and then you deposit the silicon nitride on top at the 1100 angstrom, right? And then you etch locally, and then you do the oxidation to form a Bursbig and things. Okay, do you remember in the locus process? In that case, we are in the situation where we have to etch the silicon nitride, which is deposited on top of the silicon oxide. Can you turn on the light for a minute? In the locus process, for example, in the silicon, we form a silicon oxide, 300 angstrom, as a base oxide, we call this. And then we deposit the 1100 the silicon nitride, 1100 angstrom silicon nitride, and then we mask this thing with a photoresist, and then we have to etch the silicon nitride, which is deposited on the silicon oxide. Now, if you want to use the barrel type reactor and then use the gas CF4 with the O2 addition to accelerate the etch rate, for example, then it says the selectivity is a 41. So that means the etch rate of silicon nitride is 4 times faster than the silicon oxide. So we begin to etch, and then we etch the silicon nitride 1100 like this, and then we do not have to stop the etching process exactly at the time that the 1100 the silicon nitride is etched, because the etch rate of silicon oxide is 4 times slower than the silicon oxide. So we are safe, right? So this selectivity is really important, really important. And the fourth one is the margin. It's just marginal. It's not safe enough. But as you can see in the etched polysilicon and the silicon oxide, then we can use this gas, plasma gas, and the selectivity is 20 to 1. So this means that we just put it in the chamber and then just wait until the polysilicon is entirely etched. Then the bottom layer, silicon oxide, is not going to be etched at all because the etch rate is 20 times slower. Okay? That's how you read this. Etch plasma, silicon nitride, and aluminum is infinity. So you can just put it in a chamber and then live there for a long time to complete etch of the silicon nitride, and it is safe. Silicon oxide and aluminum, and etching silicon on the resist 100 to 1. So the photoresist can be used as a mask. Okay? That's how you read this table. Okay, we turn off. The RF plasma, it does have a DC mode there. Now let's see. Let's move to the planar type reactor. Planar type, in plasma etching in a planar reactor, the wafers sit on a grounded electrode in the plasma. It just look like this. Okay. This is grounded, and then you place your wafer to be etched, and then the distance between these two electrodes is very close compared to the barrel type reactor, and the distance is very close. And the important thing is relatively high pressure, which is a 0.1 torr. Okay. In the barrel type reactor, the pressure was 1 torr, about 1 torr. The atmospheric pressure is 760 torr, right? And if you want to go for the barrel type reactor, the pressure is 1 torr. And if you go to the planar type reactor, now is 1/10 of the pressure, 0.1 torr. Okay? So we have a relatively high pressure here, and the distance is short, because the short-lived plasma, short-lived radicals plays an important role in the planar type. Now let's read this. RF electrode will tend to take a DC potential with respect to plasma because mobile electrons reach the electrode more easily than the larger ones. Therefore, ions can be accelerated. Okay, that is the important thing. And for that acceleration, we are going to have a relatively low pressure than the barrel type reactor. Okay, short-lived neutral species can play a major role. So we are now going to have a anisotropic etching because the short-lived radicals is going to play an important role here. Okay. short-lived neutral species will give you less undercutting, right? And almost the vertical walls are possible. That means we are going to have isotropic etching. Now, even with the planar type, of course, we can have a long-lived species if you use chemicals like this. Okay. So true anisotropic etching is only possible with ions. Physical etching, and this plays a minor role in a plate, parallel plate plasma system. Okay, plasma processing in a parallel plate reactor. You can have this, and then you have a selectivity like this. And in this case, the selectivity is more important because it's anisotropic etching. And you are going to have some physical collisions as well. Now, in a plate reactor, advantages almost anisotropic. It says almost. The next topic that we are going to discuss is RIE, reactive ion etching. And reactive ion etching, you're going to have more anisotropic etching than the planar type. So it says just almost anisotropic, except for throughput. Disadvantages: processes are critical. Photoresist erosion means the photoresist etching is sometimes it is a limiting case. The faster etching of the photoresist, and the dimensional control is better than the barrel type reactor. Okay, that is the planar type reactor, and then the barrel type reactor, the applications, you have to see these applications. The barrel type reactor is the most cheapest one, but it has proper usages, like a stripping photoresist. You don't want to pay a lot of money for just stripping the photoresist after the etching. So stripping the photoresist, in old days we just put the photoresist into the chemicals. We use the wet etching. But as we discussed in the wet etching, the disadvantage of wet etching is that it has many contaminated chemicals to be wasted, right? So in a recent VLSI process, we use dry etching for the photoresist stripping. And for that, barrel type reactor is the most suitable equipment. And the locust process, silicon nitride etching, okay, we use a barrel type reactor. That's much better. Etching a plasma over aluminum and isotropic etching, if you need isotropic etching, sometimes you need that, then this barrel type reactor is going to be used for that. Planar type reactor is it's mostly used in the laboratories. It's simple, but it can have some of the characteristics of RIE, which is most popular in the industries. Okay. So next week, let's discuss about this RIE, which is most popular in the industry, and ion milling machine and spider machines. Okay.